Hi, Saints. This is Mr. Matthew Lim speaking. Today, I will be delivering the first lecture on direct current circuits. Let's look at the assessment objectives for this first lecture. A. Recall and use appropriate circuit symbols. B. Draw and interpret circuit diagrams containing sources, switches, resistors, ammeters, voltmeters, and any other type of component. And E. Solve problems involving series and parallel circuits for one source of EMF. Without further ado, let's look at the lecture content. DC stands for direct current, and direct current doesn't mean that the magnitude is constant. It simply means it flows in one direction. For example, look at graph A. Suppose I called one direction as positive, and I have a graph showing a varying direct current. Magnitude is changing, but direction is the same. Now for the second graph, I have a negative direction. Magnitude is changing, direction is always negative. And the third one, direction is positive, magnitude is constant. So a direct current simply means that the current flows in one direction in the circuit. Now, a simple DC circuit consists of sources of electrical energy, for example, a battery source, resistors, as well as switches, and simple measuring instruments such as voltmeter and ammeter. Let's start with looking at the circuit symbols. All right, probably you have seen many of these symbols before. I would like to highlight one symbol that is probably not so common to you. That is the power supply. Normally, if the examiner were to draw two dots with a gap there, it refers to a power supply, and very often the value is also given. Let's take, for example, 3 volt. Okay, so the magnitude of the voltage is given. And there are other symbols that you need to familiarize yourself. You have to memorize them, I'm afraid. And there are actually three symbols that are not commonly encountered for A level. The three symbols are microphone, um, antenna or area, and the third one is the capacitor. So the rest of the symbols are usually used for A level circuit diagrams. Okay, let's look at the first principle called the Kirchhoff first law. You may pronounce it as Kirchhoff, it doesn't matter, but I prefer to pronounce it as Kirchhoff's first law. It simply means that the sum of currents entering any junction in an electrical circuit is always equal to the sum of currents leaving the circuit. It means that if I have current flowing into the junction, so the dot here represents the junction, it must be equal to the current flowing out, such as this. In must be equal to out. So this is based on the principle of conservation of charges. So let's look at example 1 to see whether we are able to apply this concept easily. Okay, suppose I have an equation I1 plus I2 equals to I3 plus I4. It means that two currents going in, two currents coming out, right? So if I look at A, I notice that there are actually three currents going in. So it violates the equation. The equation shows two current going in and two current coming out, of the reverse, right? But A has three currents going in and one current coming out. So it violates the equation. B, B has three currents coming out. Okay, three currents coming out, one going in. So again, it violates the equation. And then if you look at C, C is the right answer. Two going in and two coming out. So it follows the equation I1 and I2 going into the junction, I3 and I4 coming out. So it's correct. D is wrong because all currents are going into the point, but nothing comes out. So the answer is simply C, right? Okay, let's apply Kirchhoff's first law to example 2. So even though the solutions are given already, this is the solution, but I'm going to go step by step to explain this to you. Suppose the main current is 8.4 here. Look at the main current coming out from the battery, 8.4. 8.4 coming out, and when it reaches the junction here, it will split into 3.7 and 4.7, because 3.7 plus 4.7 is actually equal to the current going in, 8.4. And then the two currents will combine, and eventually IB should be the same as 8.4 because it is 3.7 plus 4.7, giving you 8.4. Then it reaches a junction. IC is given. IC is given as 1.3. Okay. If IC is 1.3, then I deduce that ID should be 7.1 because 7.1 plus 1.3 gives you 8.4, which is flowing into the junction. And then 7.1 microampere reaches a junction. It will split into 2.4 and 4.7, i.e. is 4.7 because 4.7 plus 2.4 gives you 7.1. So 4.7 plus 4.7 is this one. 4.7 plus 2.4, this 2.4, and then plus 1.3. That will give you the main current 8.4. That's how you calculate. Okay, so it's not difficult. You just have to do it step by step, following the what is recommended here, and you should be able to understand example 2. Okay, we are going to look at Kirchhoff's second law, which is actually basically a law of conservation of energy. Suppose we look at this example with two resistors in series connected to an EMF source. So the power source is actually supplying energy to the two resistors. So what goes in must be dissipated um, at the resistors. So we have power supplied by the source, which is IE, equals to the power dissipated by the resistor. Both resistors experience the same current because of a series circuit. So we are able to get this expression E equals to V1 plus V2. So Kirchhoff's second law, although it's stated like this, that the total potential rise equals to the total potential drop, it simply means that the EMF, which is the supply, is equal to the sum of the PDs. Okay, you sum the PDs. So the sum of PDs in this case is V1 plus V2. Okay, so EMF on the left hand side is actually the supply. V1 and V2 are actually the usage. Okay, the supply and usage. Okay, so just have this idea. Work example 3. So suppose we apply Kirchhoff second law to example 3. This time instead of two resistors, we have three resistors in series. So we have R1, this R1, we call this R1, R2, and R3, right? So there will be a PD across each of these. Okay, so I will write the PD V1, V2, V3. This is a PD across each of these resistor. Okay, so the PD across this resistor must add up to be equal to the EMF. So since it is a series circuit, the current is the same through each resistor. So I write a formula based on Kirchhoff's second law, which is this one, Kirchhoff's second law, right? So EMF equals to V1 plus V2 plus V3. Okay, so using this concept, I'm able to get the current, which is 0.002. So now my V1 turns out to be 0.2 volt, V2 1.2, and V3 0.6. Now, if I add up this figure, if I add up these three figures, I will get 2 volt because the sum of EMF, or rather the EMF is equal to the sum of PDs. Okay, EMF equals to sum of PDs. So this is Kirchhoff's second law, right? So I sum up the PDs like this. These three PDs I add up, I will get 2 volt. Okay, now I want to introduce to you the concept of potential, because you already know what a potential difference. Potential difference, as you can see here, for the first resistor, the potential difference is 0.2. Second resistor, potential difference across it is 1.2. And for the third one, the potential difference is zero point 0.6. Now I want to introduce the concept of potential here. So the concept of potential arises when I earth a certain point in the circuit. What do I mean by earthing a certain point? Earthing a certain point means I connect a certain point to earth, and therefore that point uh, is having 0 volt potential. That means you assign 0 volt potential to that earth point. So I'm going to modify figure 3a and put it in figure 3b. So I have the same circuit, but this time I earth point O. So if I earth point O, the potential at A is actually 1 point or 0.2 volt above 0.2 volt above O. So that's the potential at A. What about potential at B? Potential refers to one point, unlike PD. PD is across 2 points. So potential at B, in this case, is actually 1.2 volt below 0. So it's negative 1.2 volt. Potential at C, which is zero point 0.6 volt below potential at B, and it is actually 1.8 volt below potential at O. Okay, so if you look very carefully, point C has a potential 1.8 volt below the potential at O, which is 0. Okay, this is 0 volt. At Earth is 0 volt. But the PD remains the same. PD across resistor 1, 2, 3 remain as before. Now, suppose I shift the earth point to B. Suppose I have another example. I shift the earth point to B. Okay, this point I call it earth. So VB will have 0 volt potential because it's the earth potential, right? Then VA will have what? VA will have a positive potential, which is 1.4 volt above earth. Okay, what about VO? VO will have a potential 1.2 volt above earth. Okay, what about VC? VC will have a potential which is negative 0.6 volt above earth. All right, okay, so that is when you connect earth to point B. So is everything okay? So that's the concept of potential. Potential depends on where you earth the circuit. Potential difference is independent of where you earth the circuit. Okay? All right. If you draw a graph based on the potential when you earth it at O, the graph will show VA is having a potential of 0.2, VB is negative 1.2, VC is negative 1.8, and that is shown here, right, in this graph. So you have to familiarize yourself um, with the concept of potential here. Okay, work example 4. Suppose I give you 3 resistors in parallel. Now I have the resistor R1. Maybe I call the first one as resistor R1, the second one resistor R2, third one resistor R3. Okay, three resistors. So um, I'm able to write an equation like this here because in a parallel circuit, the EMF across each resistor is the same. So in this way, I'm able to calculate the current through each resistor. This is the current through each resistor. And if I combine all these three current, I will get the main current I1. So this is basically using Kirchhoff first law. Okay, this Kirchhoff first law, where where the main current is equal to the sum of the current in the branches. Okay, so applying Ohm's law, I'm able to get the combined resistance of the three resistor R1, R2, and R3. So 153 is actually the effective, or we call it the combined resistance of R1, R2, and R3. Okay, example 5. Example 5 is more challenging. So a battery with an EMF of 20 volt and an internal resistance of 2 ohm is connected to resistor R1 and R2 as shown in the diagram. You can see R1 and R2 are in parallel. A total current of 4 ampere is supplied by the battery and R2 has a resistance of 12 ohm. So this one we know. This is 12 ohm, all right? 12 ohm. This is known. So the internal resistance 2 ohm is actually small r, right? So how do I apply Kirchhoff's second law? So we know EMF is actually sum of PDs, okay, in a loop. So I will consider this loop. So let me indicate my loop. Suppose I consider this loop, okay, the outer loop. Okay, if I consider the outer loop, my EMF E is actually equal to the PD. PD, which is the main current. The main current is 4 ampere multiplied by the internal resistance 2 ohm, right? So that will be the PD across here. Okay, 4 ampere is 4 ampere multiplied by 2 ohm plus this one. This is, I call it I2. This is I1. Because it's the upper loop or outer loop, so it's I2 times 12, right? And the EMF is given as 20, right? So EMF is 20, 20, okay? So in this case, if I were to manipulate this, my I2 will turn out to be 1.0 ampere, right? I2 will turn out to be 1.0 ampere. So when I2 is 1.0 ampere, I know actually I know the PD across AB already. Look at PD across AB. PD across AB is actually I2 times R2, right? Is also equal to I1 times R1, right? So what is I2 R2? I2 is 1.0, R2 is 12. I1 is what I want to find. Or in fact, I1, oh, I actually know I1 because if I apply Kirchhoff's first law, if I know I2 and the main current, I1 should be 3. Okay, how do I get 3? So look at here, the junction law. Look at the junction law. 4 ampere is split into I1 plus I2. But I already know I2 as 1.0. So I1 should be 3. Okay, I1 should be 3. So in this case, I'm able to calculate R1. Okay, 12 divided by 3, I got 4 ohm. Okay, that's 4 ohm. So you may want to take a snapshot. I'm going to erase this simple solution here. So actually, I expand the solution to make it clearer. So how do you find the power supplied to each resistor? Power supplied, you use I squared times R. Oops, this is, okay, I squared times R, all right? I squared times R, so I have 3 ampere square times 4, so 36 watt dissipated in resistor R1, and 1 ampere square times 12 watts dissipated in R2. Okay, so this is the solution. Okay, so we are going to do the last question, and then after that, that is the end of the first lecture. Okay, this uh, graph shows two resistors um, behave as you increase the PD. Suppose I have two resistors in series, right? So let me draw the two resistors. Oh, I already have a diagram here, so I don't have to draw. If I have two resistors in series, so suppose this is resistor, um, I call it resistor X, this is resistor R, resistor X and resistor R in series. So the current through it is the same. So if the current is zero point 0.3, so if it is zero point 0.3, then I will draw a line from 0.3. Okay, and then the PD across X is 1, PD across R is 1.5. So this 1 volt, this is 1.5. So the sum of the PD equals to the EMF, all right? Sum of the PDs. So if I sum the PD, it is therefore 1 plus 1.5 here. I add these two, I get the EMF, 2.5, right? Now, suppose I have a parallel circuit. If I have a parallel circuit, okay, parallel. So if I parallel circuit, then the EMF is the same across each resistor. This is X, this is R. Okay, the EMF is the same. So I already know the EMF as 2.5. So I will go to the graph 2.5 and it hits 0.5. Okay, hits 0.5 here. Look very carefully. 0.5. So that means through each of these, I have 0.5 ampere, 0.5 through each. So the main current is actually the sum of the individual current, which is 0.5 ampere plus 0.5. So the current through the main circuit is 1 ampere, right? So that's how I get 1 ampere here. Okay, so today we have learned Kirchhoff's first law and second law. We have learned um, the circuit symbols, and we also learned um, how to apply um, Kirchhoff's law as well as Ohm's law in various situations. So in the next lecture, I will continue with combining resistance of two or more resistors in series as well as in parallel. Okay, thank you very much.